Okay, good morning. So good news, we have another midterm coming next Friday. As I promised in the beginning of the semester, we have 2 midterms. The next one will be on the 4th of November, which is next Friday. The coverage of the midterm is already posted in Brightspace, so you can look it up. And basically, it will cover this lecture, next lecture, and perhaps Monday's lecture, I think. Okay, I think. The following few lectures will have a lot of calculus, so I'm not going to test you on anything extremely difficult, okay? So, but there will be some basic problems I really want you to be able to do it, okay? And I will tell you explicitly of what kind of problem that I am going to ask you next Friday. So please work on those problems. Okay, so that's a hint. There are a few lectures, I think 4.4, which I decided to skip this semester, and so those will not be tested. So if you look at the syllabus for midterm number 2, you will see each section very explicit, which section is included, which section is not included. So you can look at that. So same format as before, 5 true and false, 5 multiple choice, and this time only 2 questions. Okay, only 2 questions, not 3 questions. So that's the plan. Is it good? I hope this is shorter this time. Okay, so let's go to the material. Now, clearly I wasn't very awake last time, and so I said something wrong. So I want to make a correction. And the correction is the following. There are 2 concepts. One is called the uncorrelated. Okay, of course, I'm talking about 2 random variables. And then the other concept is called independent. They are 2 different concepts. Now, what is uncorrelated? If I have a pair of random variables x and y, uncorrelated means that if you take the expectation of x and y, the product of x and y, if you can write it as the expected value of x times the expected value of y, then the pair of random variables are called uncorrelated. Independence means that if you look at the joint distribution P of x and y, if the joint distribution can be factorized as a product of 2 marginal distributions, then you say that the pair of random variables is independent. Now, the direction is that if you have this, you can get uncorrelated. But if you start with uncorrelated, you are not guaranteed to get independent. And here's a very simple explanation, because if you are independent, then what is the joint distribution? So the joint expectation. Well, the joint expectation would be the summation of x and summation of y, and then you have x and y, and then your px and y. Right? So if they're independent, then this can be written as a product of px and py. Then literally you just have x of px and sum, and then you have sum of y and py. And the first one is expected value of x, the second one is expected value of y. Okay, so that is the reason why if you have independence, you're guaranteed to get uncorrelated. And just because the expectation is a summary statistics of the distribution. So if I give you the distribution of course you can get the expectation. But if I give you the expectation, which is a summary statistics, then you cannot go backward and say something about the factorization of the PDF. So that is the reverse direction is not true. Okay, so that's the difference between uncorrelated and independent. Independent can give you uncorrelated, but uncorrelated doesn't give you independent. Now, what I was wrong is that I said expected value of xy equals to 0. That is not uncorrelated. Okay, so when will you get this to be uncorrelated? If your random variable x and y, they have 0 mean, then having this is enough to say that it is uncorrelated. The reason is that if the expected value of x equals to expected value of y equals to 0, so you have 0 mean, then this expected value of xy, okay, if there's a 0, then because this is 0, this is 0, then it will be also equal to expected value of x and expected value of y. So this is also uncorrelated. Or in other words, the better way to think about it is that uncorrelated means that your covariance of x and y is 0, not the joint expectation. Okay, because you always have this mean involved in the random variable, unless you talk about 0 mean random variables. Okay, so that's the definition. Is it better now? Okay, so that's the difference between these two concepts. Any questions? Okay, so now let's move on. So in this lecture, and also the next lecture, I want to talk about a concept called a conditional distribution. Okay, conditional distribution. So conditional probability, I guess we all understand, which is that if you have an event A, you have an event B, you say A given B, and we remember that it is just the probability of A and B divided by the probability of B. Correct? So that's the concept of conditional probability. And the pictorial illustration is that there are two events, A and B, and now you're looking at the probability of A happening given that B has happened. So you're looking at this intersection over a smaller set in the sample space, which is called the set B. So you're looking at this ratio of the intersection over B. So that's what we call the conditional probability. Now, what do I mean by conditional distribution? So you look at the symbol. Okay, you look at the symbol. Is actually pretty easy to understand. You have random variable x, you have random variable y, PDF, okay, or PMF. Can anyone make a guess of what is the ratio? Okay, so this is the PDF, right? So here is a probability of event A and event B. And so you can write it as the event of A and event of B divided by the event of B. So if I rewrite this into the form of PDF or PMF, either way, can anyone make a guess of the definition of this conditional distribution? Just wild guess. Yes? Okay, you can graduate now. Okay, fxy over fy. That's it, right? It's as simple as the original definition of the conditional probability. The only difference is that now we're talking about the PDF or the PMF, and literally it's just the ratio of the joint divided by the marginal. So when you have this PDF involved, right? So let's look at this PDF. This is a PDF, P, X, and Y. Okay, so before I do that, let me remind you. If I have a PX, what are the two typical questions I can ask you? One, I can ask you what is the probability of X in a set A. The other question I can ask you is that what is the expected value of X? Correct? So I tell you the PDF, I tell you the PMF, These are the typical things I can ask you. Well, calculate the probability for me, or calculate the expected value for me. It also means that calculate the variance and other high-order movements, right? So these are the two typical questions I can ask you. Now, if I replace this PDF by the conditional PDF, which has this ugly ratio form, but never mind, you have this PDF here. Guess what I can ask you? It's still the two things. Okay, it's still the two things. What are the two things? Number one, I can ask you what is the probability that X is in A, but with the condition, right? This conditional probability. That's a condition that Y is taking a value of small y. And conditional probability, of course, that's a condition, right? You got to go with that. And I can also ask you the expected value of X given that Y equals to small y. Okay, so if you understand what is going on in the original case, I tell you the PDF, well, you just integrate over the set A, you get the probability. I give you the PDF, and then you integrate, you can get the expected value of X. So both can be found. Now, if I give you the conditional PDF, you can also find me the conditional probability, and the conditional probability will still be this event A, but given that the other random variable Y takes a certain state. I can ask you what is the expected value of X given that Y takes a certain state. So this is the same thing. Now, how do you do this calculation? It will be pretty intense if you look at the equations, but let me give you a summary. So if you work on the fx case, how do you calculate the probability of X in A? Can anyone remind me? Integration. Can anyone remind me how do we calculate this probability? There's a fx here, there's a dx. Integrate over something, the set. What am I integrating over? A, okay? So I'm integrating, I have this PDF, and I have this set A, and then I want to find the probability. If you're not following, just think about probability that X is between A and B. Then, of course, you integrate this fx dx from A to B, right? So that can give you the probability. So this is example. So this is how you calculate the probability from the PDF. Okay, so now how do I do this fx given y? Let's make a guess. I want to find the probability of X in A given that Y equals to a small state of small y. Okay, so what should be the probability? Well, let me tell you, it is still the integration. It is still dx, not dy. Okay, pay attention. You're integrating dx, exactly the same as this. Okay, exactly the same as this. You're still integrating over dx. You still have a set A here. But what should I put into this integral? Well, here you put fx, and here you should put f of x given y. Okay, so that's the definition of probability of X in A given that Y equals to a state of small y. Now, how about the expected value? The expected value of X is integration X times fx dx, and then you need to integrate over the entire sample space from minus infinity to infinity. So this is the definition of the expectation for one random variable. Okay, how about this case? Expected value of X given Y equals to small y. What is the definition? Well, it is the integration. It is still dx, right? Whatever you have in the original case, just copy over to the new case. And then you need to integrate over an entire sample space. Okay, that's an x because you're talking about expected value. What should be the PDF you put in? F of X given Y. Okay, so far I haven't told you what is the meaning of that, but just remember the analogy between the two. Whenever you see this probability of x in A given certain event has happened, just replace your PDF by that conditional PDF. Whenever you see conditional expectation of x given something has happened, just put that conditional PDF. Okay? Whatever you do in the original case, do it in the conditional case. Replace the PDF by your new PDF. Okay, so that is an extremely, extremely important summary. Why? Because very soon you will see variables x and y and y and x and z and z and y and z, and, okay? And then you start to integrate. And then you got lost because from time to time you forget that it should be dx. You may suddenly put a dy here, and then it doesn't integrate to 1, and then you cry, okay? So here is a very important summary page. Just remember, if you are integrating over the variable x, you're looking at the event of x, it has to be dx. And then when you have condition, just replace the PDF by the conditional PDF. And that is the key thing to grab. Okay, so are you ready to go into more details? Okay, remember the summary. So let's talk about the conditional distribution. So conditional PMF and PDF, pretty much the same thing. Okay, so let me give you this example. So suppose you have 2 coins. Okay, so let's look at the description below. Suppose you have 2 coins. X equals the sum of coin 1 and coin 2. That's a sum. So what would be the sample space for X? Well, the coin can be either 0 or 1. So the sample space of X will be 0, 1, 2. Okay, great. So this is the sample space, and assuming that it is a fair coin, we can even just plot the PMF. So to get 0 for the sum, it will be 1/4. Get 1. I think it is 1/2. Get 2 is 1/4. Right? Am I right? Okay. So that's a PDF for X. Y is the first coin. Okay. So the Y is just 1/2 and 1/2, 0 and 1. Okay. So this is X and Y. Okay. And now I want to look at the PMF of X given Y. I want to look at probability of X given Y equals to 1. Okay. It's a little bit complicated, so let's walk through this thinking process. So, so there are 2 variables, right? So 2 variables, dependent. Okay, so you have X, you have 0, 1, 2, and then Y, you have 0 and 1. Okay, 0 and 1. You ask, okay, what is the probability? What is the probability distribution of what is the probability distribution when Y equals to 1? When Y equals to 1. Well, when Y equals to 1, you are not looking at this entire 2-dimensional table. You're only going to look at this thing here, right? So here, this 2-dimensional table is this thing of P, X, and Y. So you have coordinates X and Y. X can be 0, Y can be 0. So you look at this point here. But now if I say, hey, let's look at the conditional probability where Y equals to 1, and then tell me the values of x, right? So you're really looking at one row. Okay, so now let's fill in some numbers. Let's fill in some numbers. If y is 1, okay, just think through it in your head. If y is 1, what would be the probability of getting x equals to 0? 0, it would never happen because y is the first coin. If your first coin is already giving you a 1, what is the probability that the sum will be 0? No way. Okay, so you get a 0 here. And then what is the probability that you're going to get a 1? Okay, so what is the probability that you're going to get a 1? Well, you think about this. So if y is already 1, so what are the chances? What are the other possibilities? So if y is already 1, then that means the second coin can be either 0 or 1. Okay, y is already 1. So the first coin is already, first coin is already 1, and then the second coin can be 0 or 1. So if you get 0, then if second coin is 0, then you will just get 1 again. If the second coin is 1, then you get 2, right? So, and then probability of getting them would be half and half, right? So you get 1/2 and 1/2. Okay, so you can see that this conditional probability you can actually construct. You can construct the conditional probability by looking at this table and then putting things together. Okay, so let me work on another example. So here is example containing 4 states, x and y. And in this case, the probability masses, they're given to you already. So this is a 2D PMF. And I want to find, what do I want to find? I want to find, y equals to 1. Okay, so I want to find what is the probability that x can be any state, but given that y equals to 1. Or in other words, I want to find, this is the PMF, right? So x given 1. That's just a shorthand notation to define this probability. So what is that? Well, when you look at this an array of numbers, y equals to 1. Okay, so that's the condition. Y equals to 1. In this table, where is the set? Is it one column or one row in this array? I want to look at the event that y is 1. Now, y is here. I want to look at the event that y is 1. So that means the random variable y is already fixed at 1. Okay, I'm already just looking at that column. And I ask, hey, what is the probability distribution for x given y equals to 1? Well, I'm just looking at these numbers. I'm looking at these numbers, right? I'm looking at these numbers. So what are these numbers? Well, these numbers will be that it will be, I have 4 numbers, right? 1 over 20, 1 over 20, 1 over 20, and 0 over 20. So these are the 4 numbers. And these 4 numbers, what are they? Well, they are the probability of x okay, so y equals to, okay, this is x and 1, okay? Now, what is x? Well, I have 4 numbers, so these 4 numbers, they are x of 1 and 1, p of 1 and 2 and 1, p of 3 and 1, and p of 4 and 1. So these are the 4 numbers, okay? So they're the joint distributions, they're the joint probabilities. Now, remember that the conditional probability of x given y equals to 1, how do we define it? It is defined as the probability of x and 1 divided by the probability y of 1. Okay, so that's the probability of x and 1 and y equals to 1. Now, this x1, of course, it will be one of these four numbers. And then py of 1. Now, what is py of 1? Py of 1, that's the marginal distribution. The marginal probability can be found by taking the sum of all these numbers in the column. So that will give me 3 over 20. 1 over 20, 1 over 20, 1 over 20. So I can just sum them up, I can get 3 over 20. So I will have 1 over 20, 1 over 20, 1 over 20, and 0 over 20, divide by 3 over 20. So that will give me 1 over 3, 1 over 3, 1 over 3, and 0. Okay, so that is the conditional distribution. Do you notice one thing? That this is p of x given y equals to 1. So I'm already fixing my y equals to 1. And I'm looking at the distribution for x. I have 4 numbers. Anything special about these 4 numbers? Now, if I look at the original array, I have 4 numbers, right? 1 over 20, 1 over 20, 1 over 20. They don't sum to 1. How about here? Ooh, they sum to 1. That means it becomes a legitimate probability. Okay, there's a legitimate probability because I am rescaling my events over a new, smaller sample space, which is a space defined by y equals to 1. I am just looking at this event where y is already fixed to be 1, and then I'm looking at the probability of getting 1, 2, 3, 4. So they will give me 1 third, 1 third, 1 third, and 0. So the way to calculate this conditional probability is that you look at the table, you look at the joint, and then you calculate the marginal, and then you calculate the ratio. That will give you the conditional probability. So that's example number 1. Is it okay? Hopefully that's not too hard yet. Now let's work on another example. So this one is a little bit more involved. You have 2 random variables, x and y. Y has 2 states, 10 to the power 2, 10 to the power 4. The probability of getting this will be 5 over 6. The probability of getting that will be 1 over 6. So that's the probability for y. And now x is dependent on y. So you have x equals to some number times y, some number times y, some number times y with different probabilities. So I want to find the 3 things, right? So conditional probability, the marginal, and also the joint. So let's see, how can I do it? So I want to find the conditional probability, the marginal probability, and also the joint distribution. And clearly, I don't have access to the joint distribution by just looking at the problem setting. It's a bit difficult. But I can start with the conditional. The conditional will be x and y. Okay, x and y. Now, what should be the y? Well, I have 2 states of y, 10 to the 2 and 10 to the 4. 2 states. Okay? So if you really hate mathematical symbols, let me give you some numbers. Okay, let me give you some numbers. Okay, if you don't like this, how about this? Is it more friendly? When I was a student, I liked this more than looking at x, y, z. Okay, so can we understand these 2? So it is the conditional probability of getting an x, given that y is taking the value of 10 to the power 2. This is the conditional probability of x, given that y is taking the value of 10 to the power 4. Right? So these are easier to understand. Now let's look at them one by one. Let's look at the first one, this one. This one, I have to worry about different values of x. So of course, my x has 3 states. So from here, I can spin off to talk about 3 things. This is the probability of my x. So what are the values of x I can take? Well, if y is 10 to the power 2, my x equals to 10 minus 4 times 10, 2. So I can get 10 minus 2, right? Right? Am I right? So you have your 10 to the power minus 4 times, y is already fixed at 10 to the power 2, so you get 10 minus 2. Or I can look at 10 minus 1. I can look at 10 0. Okay, so I can talk about these three probabilities. And what are the probabilities? Well, it would be 1/2, 1/3, and 1/6 probability of getting each state. It's specified by the problem. So one way to think about the conditional probability is that by saying that x condition on y equals to 10 to the 2, you really just fix your y to 10 to the 2. Okay? Everything else just follows. So you have this conditional probability, conditional, conditional. So what do I have here? So you have your p of x given 10 to the 2. You have three values. You have, it will be 1/2, 1/3, and 1/6 for x equals to minus 2, x equals to minus 1, and x equals to 0. Okay, so this is the conditional probability when y equals to 10 to the power 2. Now I can do the same for the conditional probability that y equals to 10 to the power 4. So that will give me, again, 1/2, 1/3, and 1/6. But here, the x has to be 10, 0, equals to 10, and x equals to 10 to the power 1. So that would be the three states for the other case. So I have found the conditional probabilities, which is given by this slide. So you have when x equals to this, the probability of getting there is this number, and so on. So that would be the conditional probabilities. Now I'm not done yet. I still need to find the marginal. Oh, I need to find the marginal distribution. How do I find the marginal distribution? Well, to find the marginal distribution, I probably need to find the joint distribution first. So let's talk about the joint. So I'm done with this. I need to find these two. So the joint distribution is P of xy. P of xy is going to be P of x given y times P of y. Because this is conditional probability, this is the conditional probability times its marginal, that will give you the joint. So that's just the reverse definition of the conditional probability. So this is given to me. I need to find this. Well, all I need is to find the marginal of y. Wait a minute, do I have access to the marginal of y? I do. It is here. Okay, so what is P of y? Well, P of y, you can take two states. When it is 10 to the 2, it will be 5, 6. If it is 10 to the power 4, it is 1, 6. So I have this. Okay, so now you go back to here. You have pxy, when y is 10 to the 2, well, you have certain probability getting 10 to the 2. So you just multiply 1/2, 1/4, 1/3, 1/6 by 5/6. Then you can get the joint when y is 10 to the 2. So what I mean is the following. You will get this number, this array. This array contains x and y. When y is 10 to the power 4, then your x will have three values, 1, 10, and 100. So the probability of getting a 1 will be This 1/2 times the probability of getting 10 to the power 4, which is 1/6. So 1/2 times 1/6, then you get 1/12. Okay. All right. So okay, so let me just write it once for you. So the probability, let me just give you an example. Let's say x equals to 10 to the power 4, and y is, oh, no, wait, 1, right? So x equals to 10 to the power 0, and then y equals to 10 to the power 4. What is this joint distribution? Well, this joint distribution is the probability that x equals to 10 given y equals to the 10 power 4 times the probability that y equals to 10 to the power 4. And this thing here, according to my conditional probability, this is 1/2. It is this case when x is 1 and y, given that y is 10 to the power 4, 1. Okay, so this is 1/2. And then this is just probability of getting y to the power 4, and this is 1/6. So we have 1/6, so 1/12. That will give you this number. And you can repeat the same exercise to fill up the rest of this table. Then you get the joint PMF. Now to find the marginal PMF of x, what should I do? Well, sum. Should I sum over the rows or should I sum over the columns? Columns. Okay, wake up, guys. Okay, you sum over the columns, then you get these 5 numbers. So this is your marginal PMF of x. Now, you can do a simple check. Just check if these numbers, when they sum up, they will sum to 1. And it should. If it doesn't, then you have a bug in your answer. So it's a pretty good sanity check. Okay, great. So let me skip the next problem, okay? And I want to talk about a slightly more interesting one. So let's talk about this problem. So this is page 11. I think if you understand this problem, you sort of really understand the entire section here. Okay, so here is the deal. I have 2 classes of data points. Okay, class 1 and class 2, with disease, without disease, cat and dog, flower and building. Okay, so 2 classes of data points. They are unclustered. They are unclustered. So you see something like this. Okay, so one-dimensional distribution to make our life easier. So you see something like this. Okay, and then of course the inverse problem is that now I give you a sample which class does it come from, right? It's a classification problem. But let me reverse this question a little bit by going through the forward-thinking process, right? Then we can talk about the inverse problem. So when you have this distribution here, the first reaction is, where does it come from? Where does it come from? So I can make something up by telling you, how about this? You have one Gaussian and then another Gaussian. I tell you up front, okay? Don't challenge me, okay? Because I'm the exam maker, okay? So I tell you that there are 2 distributions. Distribution 1 for class 1 and class 2. The 2 classes. They're Gaussians. They have different heights. They have different width. They have different centers. Okay, so the mean, mu, and the variance sigma, they are different. So you start with this. This is class 1. This is class 2. Okay, so I want to assume a signal. Okay, so I have x, and I have, let me see, so y equals to x plus, I want to, this is not as interesting. Okay, so don't look at the formula. Okay, but just look at this two diagram, and then we can come back to the formula later. So you have this distribution. Okay, so I want to find some kind of probability. I want to find some kind of probability. I want to say, okay, so here is a distribution. Number one, what is the formula for this? Okay, what is the formula for this? And two, of course, this when you put them together, when you look at the thing outside, it will look like that, right? So let's say this is your y, this is your f of y, fy of y. Want to find probability that y bigger than 0, or some number. Okay, so I want to find some probability, and I want to find the expected value of y, something like that. Okay. This could be useful because if you're working on realistic problems, you know the underlying distribution of these two data sets. They come from two different Gaussians. Not that I want to ask you this question, just because your boss wants to ask you this question, right? So it's very realistic. Okay, so the first one, how do you write down the formula for this thing? How do you write down the formula for this thing? Well, you have two Gaussians. They have two different means, mu1 and mu2, two different variants, sigma 1 and sigma 2. How do you write down the distribution? So here is why I want to talk about the conditional probability. Let's look at class 1. Okay, let's look at class 1. What is class 1? Class 1 is a Gaussian random variable. It has a mean, it has a variance. So f of x given C1, okay? F of x given C1, it is a Gaussian. So it is 1 over root 2 pi sigma 1 square e minus x minus mu1 square divided by 2 sigma 1 square. So that's Gaussian. So that is class 1's distribution. What is class 2? F of x given class 2, it is 2 pi sigma 2 square e minus x minus mu 2 square divided by 2 sigma 2 square. Okay? Two different Gaussians. And you really don't care about how do they add up. You don't know. Okay? So you have two conditional distributions. And let me tell you that class 1 has certain probability of being drawn, right? So your two classes, A1 and 2, you may have 90% chance you go to a bag, you draw it comes from class 1. Just like you drive on the I-65 freeway, you're likely to see Ford and Chevrolet than see a Tesla, right? So this is just the probability, the underlying probability distribution. So let me say that the probability of getting C1 is P. The probability of getting C2 is 1 minus P. Okay? So I ask, what is the probability of, what is the distribution of X? Now, look, this X, fx, is not conditioned anymore. I'm asking an unconditioned probability. So how do I get that? Okay, so the way to solve this problem is the following. Remember a thing called the law of total probability. Okay, so you have certain event A, given some smaller events, you want to write this as a sum of these smaller events. So same thing will apply here. So you have f of x given C1 and f of x given C2. And then, what is the probability of getting C1? That is P. What is the probability of getting C2? This is 1 minus P. You add them up, you get this joint distribution. No, not joint distribution. You get this probability distribution for X. If I want to be more precise mathematically, what this is doing is f of C1, this is f of C2. So technically speaking, I am really just looking at f of x given C1 times f of C1 plus f of x given C2 times f of C2. This is a decomposition rule. If you go back to the note, which page is it? Okay, so you can see some really, really super ugly formula, okay, which you may not be able to understand what they're talking about here. But if you look at this picture here, you will know. You have conditional probability on different classes, and then I tell you the probability of getting each class. So just multiply them, add them together, that will give you the original probability that you were looking at. And so this is the formula for this. X. Okay, so this is X. So when you look at the data set, I don't tell you the underlying composition. So you're going to see this distribution. Okay? This distribution is given by this formula here. Now, of course, just put in these two equations into this formula, and then you can get a number. Okay? So then, how do you calculate this probability of y bigger than 0? How to calculate the probability that y bigger than 0? Well, pictorially, you go to this diagram, and then you draw the 0 line here. So the 0 is here, and then you integrate over the curve. But mathematically, what you would do, x, okay? X bigger than 0. So probability that x bigger than equals to 0, if I tell you that it is P of a Gaussian sigma 1 squared E minus x minus sigma 1, okay, plus 1 minus P of 1 over 2 pi sigma 2 squared. Okay, so I tell you this is the formula. Then laterally, what you're doing is that you're going to integrate over x from 0 to infinity. Then what you're doing is that you are really just going to do this probability of integrating 0 to infinity of your f of x given C1 dx. Now, pay attention. You never integrate over your class C1. You always integrate over your x. Plus 1 minus p integrate of your f of x C2 dx. And you can do the calculus by yourself. Okay? So this is the decomposition rule of calculating the probability. Now, this is here. Okay? That's point number 2. If you don't remember this formula, it's okay. Just remember this example. I think this understanding the example is a lot more helpful. And then the third question is, how do we find the expectation of x? Well, finding the expectation of x, of course, you have this fx. Then you need to do this integration from minus infinity to infinity of your fx, and then there's an x, and then dx, right? And then your fx is just the sum of these two events, so you can write it as p times the integration from minus infinity to infinity of x given c1 dx plus 1 minus p of integration from minus infinity to infinity of x given c2 dx. Now, what is this? This, I can further simplify it as the probability p times the expected value of x given c1 plus 1 minus p of expected value of x given c2. Why? Just remember the summary slide I gave you in the very beginning. Whenever you see the integration x and then there's some kind of probability, that's just the expectation. Okay, you replace the normal expectation by this conditional expectation. So you can see that there is another decomposition of the expected value of x can be written as a sum of these two conditional expectations. So by just understanding this simple example, you are good to go because you sort of really understand all the theorem here, and also the next lecture is all the theorems. Okay? If you really understand this problem, conditional expectation and also this probability, conditional probabilities, densities, it's just as simple as this. It's a decomposition. Replace everything by your conditional probability. Okay? So we will go back to this example again next time, and then I will tell you more on the expectation side, and then we will do more examples. Okay? So study hard. Okay, see you next time.